Thank you for that introduction, Roger. And good day, everybody. And thank you for coming today. I hope you've all made the effort of wearing a Panama hat and Hawaiian shirt, as I have. The theme of Quality Week is moving from compliance to performance. In the context of quality, compliance implies ISO quality standards. I'm going to expand from just Six Sigma to all the standards related to all the ISO standards, that is, related to quality. And of course, compliance implies compliance with these standards. Now, I'd like to start with a quote from the great Professor Deming. He said, ISO 9000 shows a lack of brains. I'll be talking about a number of ISO standards that relate to quality. I will show how you can do much, much better than with ISO. By way of a little bit more background, I've specialised in quality for more than 3 decades. My company makes software for quality. Our main product is Q-Skills 3D, e-learning in quality and lean. Now, you've probably seen e-learning at some point, and you'll know that it is as boring as watching grass grow. Q-Skills 3D is very, very different. We engage people in quality by making learning fun with games and interactive exercises. And as you can see, we've been very, very successful with this approach. We also have a couple of interactive 3D augmented reality products for learning about quality. One of these is free in the app stores. It's entitled The Deming Funnel. It is a lesson in how you should and should not attempt to reduce variation to improve quality. This is known as process tampering. Despite employees' best intentions, tampering or fiddling with the process can make things worse. And I still love this example where you're actually using the mobile phone to manually drop balls into a funnel that doesn't exist. And this is actually mode 3 running in auto mode. And at the end, it generates a number of graphs to show you the impact of various types of tampering. Quality. Before considering compliance to standards, we must first consider what quality means. Quality dates back at least 2,400 years to the Greek philosophers. Plato's Phaedrus said that quality was undefined and undefinable. However, industry has made it essential to define quality. Q-Skills actually has a couple of games based on historical examples of quality improvement. One of these true stories took me 2 years to track down in the archives of our state library. I'll show you some of these examples at the end of my talk. It will be a challenge for you to try and guess what was done to try to improve quality. So what is quality anyway? Now you might recognize some of these names. Firstly, we have customer's perception from economist Dr. Feigelbaum. Next, we have fitness for use by lawyer Mr. Duran Esquire. The degree to which requirements are fulfilled from the ISO committee, which reminds me of the definition of a committee, a bunch of the unfit appointed by the unwilling to do the unnecessary. According to podiatrist Mr. Crosby, quality is 0 defects. Conversely, Mr. Nakajima, creator of Lean's utterly ridiculous OEE, claims quality is 100% good. And finally, we have the laughable 3 4/10 of a defect from high school teacher and self-confessed con man, Mikhail Harry, creator of Six Sigma. All of the above definitions of quality are manifestations of quality 1870 style. Every one of these is an expression of the specification. It was in 1870 that the concept of the defect fully emerged with the development of the go-no-go gauge. This was a step of great importance, but quite lacking with regard to process improvement. An item was either good or it was trashed. There was nothing in between. At this time, the need for interchangeability of parts made good quality essential. For example, in the 1860s, in the American Civil War, interchangeability was the key in using the mini ball in both the US Springfield and the British Enfield rifles. All you needed was go, no go. That was quite sufficient. The go, no go gauge was an early form of the specification. If it was go, the specification was met. If not, it was a defective. All subsequent attempts to define quality in terms of counting defects or whether a customer's needs are satisfied or not are expressions of this antiquated quality 1870 style. Modern quality. In marked contrast to specification-based quality, Dr. Shewhart made a radical departure from traditional statistics to lay the foundations of modern quality. Professor Deming, Professor Lewis, Professor Chambers, Dr. Taguchi, and Dr. Wheeler built on his work. All these men, with the exception of Professor Lewis, were statisticians. Lewis was a philosopher. His work led to Professor Deming and Dr. Shewhart's philosophies of quality. Hence, on one hand, we have a bunch of podiatrists and high school teachers preaching 1870 quality. Now, there's nothing wrong with these professions. In fact, my wife is an economist. However, on the other side of the fence, we have a group of brilliant statisticians building modern quality. Dr. Taguchi worked with Dr. Shewhart, and Professor Deming was mentored by Dr. Shewhart. Dr. Wheeler describes himself and Dr. Chambers as Professor Deming's grandchildren. These men led to the modern definition of quality, on target with minimum variance. Rather than having a product that was either good or bad, Taguchi suggested there is some arbitrary function associated with all the costs in making a product. These costs have a minimum value at the target. There is a single tool that is essential for determining whether a process is on target with minimum variance, and that is the control chart. A control chart is an action chart. It tells us whether there is something wrong with our process that should be investigated. It tells us whether or not we have a constant system. That is, whether our data are homogeneous, and that is, whether we are comparing apples with oranges or not. Now, I picked this example because it is a slide from an accounts department, somewhere where you don't normally associate control charts. Control charts can be used absolutely anywhere. And this chart has been generated by our free MaxiQ software. The main characteristics of the control chart are an averages chart and a ranges chart. Both charts show control limits that are generated from the data. There's a histogram at the bottom that can be also used to show the specification limits. Note that control limits are generated by the process, but specification limits are set by people. Specification limits should never appear on a control chart. While control charts are based on statistics, they are not probability charts. They do not show the probability of any event. Claims of 99.73% of points in control are utter nonsense. If you see a control chart labeled with 99% or something like that, you can be sure that the author does not understand what a control chart is, nor its purpose. Control charts are economic charts. In fact, Dr. Shewhart's book describing his revelation was titled The Economic Control of Quality of Manufactured Product. Control charts indicate when it is economic to investigate something that may or may not be amiss. Professor Deming said they provide points where it will be profitable to try and determine and remove the cause of exceptional variation. Now, if we look at this example, we see some exceptional variation here. And when the accountant investigated, it was discovered that this was, I don't know if you can see it here, it was during COVID. And during COVID, people were having trouble making payments. Compliance. We saw earlier that ISO 9000 uses the 1870 definition of quality. The ISO 9000 series makes no mention of control charts, which are at the heart of modern quality. ISO 9000 completely ignores the modern definition of quality, on target with minimum variance. Control charts are pushed aside to their own standard, 7870. 7870's title says that it is a standard for Shewhart control charts. However, the authors of this standard have not bothered to read Shewhart's work. The standard is a complete mess. Compliance with such a standard leads you to nonsense. Let's take a closer look. Misunderstanding of control charts. In recent decades, there has been massive misunderstanding of control charts, as exemplified by ISO 7870, and I guess by the ISO 9000 series as well. Commercial charting products have profited from this ignorance. Dr. Shewhart said, "We never know the function in sufficient detail to set up such limits." That is, he did not make any assumption of any probability distribution associated with process data. Professor Deming once said, "Normal distribution? I never saw one." Shewhart said, "Experience indicates that T equals 3 seems to be an acceptable economic value. That is, 3 sigma control limits are not based on some statistical calculation. They are based on the economic consequences of missed signals." Dr. Shewhart's assertion that his charts do not depend on any particular data distribution was a massive shock to traditional statisticians like Pearson and that mob on the right of the earlier slide. Dr. Wheeler tested 1,143 different data distributions to validate that we do not need to know the data distribution for a process. The false claim that control charts need test of normality has lured victims to commercial charting products. What test of normality should we use? WS, QQ, Jacques Berra, D'Agostino, Shapiro-Wilk, Kolmogorov-Smirnov, Anderson-Darling, Martinez-Iglewitz, or Lilienfors, perhaps? It is not uncommon to have half the test saying agree, while the other half say disagree. Yikes. Many vendors then recommend data torture for the sin of a positive test for non-normality. Yes, we can only test for non-normality. It is impossible to see if our data is consistent with a particular probability model. We can only test for a detectable lack of fit between our data and a model. That is, no test can ever give us a green light anyway. They can only give us an occasional red light. Charting software that tosses in a test for normality for a control chart is a red flag for incompetence. And this applies to 7870 as well. Secondly, data for a process is not taken from a fixed pond. Data for processes are changing. We cannot even attempt to assign a probability model. Without a probability model, tests of hypotheses and confidence intervals are completely inappropriate. Probability theory focus on what happens when samples are taken from the pond in this image. A known universe, the pond. With processes, we don't have such a known universe. Thirdly, control chart data is very different to data in the pond or traditional statistical methods in that it takes into account the sequence of data. Traditional statistics don't care about the order of samples taken from the pond. They do not consider the sequence of the data. It is indeed fortunate that Dr. Shewhart gave us a way forward. In other words, it doesn't matter where your data is coming from and what your data distribution is, even with extreme distributions such as the exponential. It is particularly fortunate for companies because it makes control charting very, very simple. Such simplicity is less fortunate for commercial charting vendors trying to convince people how hard things are and how they need to buy their product. ISO also displays such massive ignorance in advocating tests for normality and treating Shewhart charts as probability charts, which they are not. The purpose of a control chart is to tell us when a process is predictable. That is, it tells us whether we can continue making good product or service now and into the future. Being able to make predictions is as fundamental to business. Consistent quality is essential for maintaining customers. A control chart helps us separate signals from the noise. Rather than having managers alarmed at every high or low value, control charts separate routine variation. They give us a warning when we should take action and investigate. These warnings are not intended to be absolute. You people will know that most disasters happen without warning. Having a warning, even if it occasionally gets us off our butts for nothing, is a gift. Managers should be spending more time at the work front anyway, ideally focused on talking to operators. We should aim to be like Toyota's subsidiary, Tokai Rika. They have processes that have been documented to run for months in control. Toyota, of course, uses Professor Deming's methods. XMR control charts. In 1923, Dr. Shewhart wrote, obviously, if the cause system is changing, the sample size should be as small as possible. There would be some advantage, therefore, in reducing the subsample size to unity. Jennett solved this problem 2 decades later in 1942 with what became known as the XMR chart. The power of XMR charts is that they can be used for count data as well as variable data. Traditional count data charts, such as C and U charts, assumes your data follows a Poisson distribution. P and NP charts assume your data is binomially distributed. If your data does not follow these distributions, you get the wrong answers. In contrast to these, XMR charts do not assume a distribution for the data. That is, you can't get wrong answers. Unsurprisingly, the relevant ISO standard 7870 fails to grasp this. XMR charts are the Swiss Army knife of quality. They can be used for any type of data and are almost as easy to use as a run chart. Operational definition. Before charting anything, we should always first consider Professor Deming's operational definition. It has 3 steps. What do you want to accomplish? By what means? And 3, how will you know when you have accomplished your objective? For example, in the case of COVID, the answer to question 1 might be, we're trying to find how fast the disease is spreading. The answer to question 2 should be the run chart. Run charts are ideal for charting trends. The purpose of control charts is not to look at trends, but to ensure that our process is predictable. We already know that COVID is not predictable. Control charts would be a poor choice. ISO gives no such guidance. Histograms. Histograms are a very powerful way to look at your data. ISO completely ignores them. To see what we can do with a histogram, let's have a look at a data set on a control chart. And this is again charted with our free control charting product, MaxiCare. Now this data looks pretty good. If this was a control chart from a supplier for their product, we might be quite happy. Now let's have a look at its histogram. Firstly, here's the histogram for this exact same data, charted using the commercial charting product, Minitab. It shows the ubiquitous and utterly meaningless normal distribution drawn over the histogram. This useless curve hides any messages the histogram might be telling us. It tells us nothing. We have no idea what the data distribution for this chart might happen to be. As Dr. Shewhart and Dr. Wheeler have proved, it is irrelevant and should never appear on a histogram. We could just as easily have drawn the famous author Antoine de Saint-Exupéry's boa constrictor swallowing an elephant on the chart. And by eye, it actually looks as though it fits this data better than the Minitab's normal distribution. The type of data distribution is irrelevant. The best approach is always the simplest that gives the required insight. Minitab costs you $1,850 per person per annum. Let's have a look at what our free control charting product does and how it does provide insight. We have a slider under the histogram that we can drag to see the message that the histogram is telling us. So let's just let this run. And we reach a point by moving this slider, we can see that the data is chopped off at the left on the lower spec limit. It's had below spec product removed. There's a very good chance that the supplier is relying on buyers living in the past in 1870 quality mode where only the spec is considered. This is not good product. We must meet specifications, but meeting specifications alone isn't enough. The secret of quality was revealed to Ford in 1985 in their famous transmission study. Ford compared their transmissions to identical ones made by Mazda. Ford focused on what they said called building to print, that is, building to specification. Mazda focused on reducing variation. Mazda's variation between some parts was so small that Ford couldn't even measure it. The repair frequency of Ford transmissions was 5 times that of the Japanese. Customers preferred the Japanese. Ford realised that the Japanese had significantly better fit, function, cost, and weight because of their focus on reducing variation. Sadly, Ford has been slow to learn. 40 years later, and they are still using a specification-based approach to quality. Ford, like many others, have fallen even further behind the Japanese. More compliance. Another quality standard is ISO 10009. It is an alphabet soup of everything from turtle diagrams to the utter farce of OEE. It is everything the committee could even think of vaguely related to quality. You pay hundreds of dollars to get nothing but a list of 55 tools. In fact, you could buy all of Dr. Wheeler's books on quality for about the same money, depending on where you shop. This standard says nothing about how, when, where, why, or whether to use this mishmash. The thought of complying with such a standard is laughable. Despite its list of 55 tools, the ISO committee ignores the companion tool to control charts, histograms. There's no mention of this tool for quality. More tools do not mean better quality. Nothing has changed from when Professor Ishikawa pointed out that the basic tools, if used wisely, are all you need. To make matters worse, ISO 10009 tosses in Six Sigma, making the utterly laughable claim that resulting defect levels will be near zero, even with shifts in the process average. That is, it claims that a process can be wildly out of control, yet be near perfect. There are an additional two separate standards for Six Sigma, ISO 1353 and ISO 18404. These standards are the greatest farce of all. Compliance with these standards is a road to disaster. Let's see why. Six Sigma. An obscure university dropout and Motorola employee named Mr. Bill Smith was a strong Deming advocate. He correctly stated that Professor Deming's 14 points of management are a way to move organisations to prosperity. However, contrary to Deming's advice, he tampered with his moulding process. And you remember we looked at the video on tampering at the start of my talk. Tampering resulted in a quality disaster with a process mean that shifted as much as 1.5 sigma. Mr. Smith's buddy, high school teacher, Harry, was clueless about quality, but saw the potential for a mammoth fraud. He proved that all processes in the world were wildly out of control, just like his buddies, based on the height of a stack of discs. Just an utter farce. Mr. Smith's 1.5 sigma shift blunder became goodness. It became what Harry called the pillar of Six Sigma. The next slide shows what a Six Sigma process looks like, an out-of-control disaster. Harry had no idea what a control chart was and never even mentioned control charts in any of his bombastic baloney. Now, utter trash like this would never have gone anywhere if Harry had not realised he needed buy-in from a CEO who was clueless about quality as he was. Neutron Jack CEO, Neutron Jack GE CEO, was the perfect victim. Jack described Harry as a madman, and he said that no one in the room had any clue what Harry was talking about. But Jack handed over $1 billion anyway. A scam was born. Harry was later to admit Six Sigma champions are con men. All you have is smoke and mirrors. Six Sigma is a snow job. He admitted it was a fraud. The results were inevitable. 91% of Six Sigma companies failed. Companies like Ford claimed success. However, a long-term study at Ford covering hundreds of supposedly successful Six Sigma projects showed an average of 1 in 5 parts defective after improvement. Makes you wonder what the unsuccessful ones were like. A Ford engineer actually said to me that they had observed the 1.5 sigma shift in all their processes. They were compliant with ISO 13053. This poor fellow did not realise he was saying that all their processes were an out-of-control disaster. Motorola. Motorola once had it all. In the late 1980s, Motorola bought into the Six Sigma scam. Motorola's 1987 annual report describes their goal of achieving Six Sigma, whatever that means, by 1992. Six Sigma destroyed quality. Motorola collapsed. From a peak of 150,000 employees in 1990, it was forced to sack 90% of its staff to become a mere shadow of its former self. By 1998, the year of the last mention of Six Sigma, Motorola was running at a loss. Other impacts of Six Sigma were even worse. 9 of Deming's 14 principles of management relate to employees. For example, point 9 is break down the barriers between workers and management. Six Sigma's coloured belts were a brilliant marketing trick that served to alienate workers. They exacerbated the divide between management and workers. Focusing on cost cutting destroyed quality as well as people's lives. At GE, for example, any employee who didn't make Harry's ridiculous annual cost-saving target claim of $1 million per annum per person was sacked. Inevitably, data fraud became endemic. Fake it or risk joining the 110,000 sacked employees. Gullible companies slowly learned at their cost that if you focus on cost cutting, quality goes down the toilet. As doctors Deming, Taguchi, and Wheeler showed, focus on quality and costs are minimized. You remember the Taguchi curve. In summary, Six Sigma is built on a self-confessed con man's fraud. Every aspect is the opposite of quality. Compliance with Six Sigma ISO standards is a road to ruin. Training. Quality is for everybody. It is important to engage every employee in quality. Every employee should be trained in the way Toyota trains its employees. Toyota's worker quality circle improvement teams have made over 2 million process improvements, saving billions of dollars. They focus on quality and cost cutting as the result. Every employee should be involved in quality, not just you people here. So how do you engage everybody in quality, particularly when they may be less enthusiastic about quality than you people? Our approach to engaging employees is to let them have fun. Q-Skills 3D uses games and interactive exercises to teach control charts, histograms, and every other aspect of quality. Now, it takes about 8 hours to go right through, but I'd like to show you one quality improvement example from a century and a half ago. And I think I still have a little bit of time, don't I, Roger?
Yes, you do.
Okay, let's just okay, can you all see that okay? No.
Yes.
So you can see that?
Yes.
See the menu? Okay, this is Q-Skills 3D, and we start off with very basic things like how to use the course. It might seem trivial, but we're working in a 3D environment. So if I move the mouse, it moves things. So we start very, very simply so that any employee, even employees that may have never used a computer before, can work in this 3D environment. And we come down to control charts. We introduce what a control chart is. We give a description, an interactive example. And here we have a game. And this is one of the many games in Q-Skills. And this game is actually a true story of historical improvement that happened about 150 years ago. And it took me a very, very long time to find out the source of this story, but I found the true story in the archives of our state library. So we're on a ship at sea. And if I move the mouse, we can aim. And this is exactly what used to happen back in days gone past. If you wanted to shoot the enemy ship, it wasn't easy. And all I've got to do is click the mouse to fire. Okay, let's have another shot. If I'm very, very lucky, I may get a hit here. And it's back in the day, they had about one shot in 50 that was successful. And it's probably about the same in this game. It's much, much more difficult than it looks. I don't know how many times I've played this, but let's have another go. And hopefully I can show you what a hit looks like. We get 7 shots, and we played this game again in the previous section on histograms, and we learnt how a histogram can be used to show this data. And in this example, we're going to chart this data using a control chart. And hopefully, I'm very close. Now, hopefully I can get a hit on the last shot. You shoot like a landlubber. Well, that's about right. It shows the results from when I played the game in histograms. And here's where I'm playing the game in control charts. And it shows the results on a XMR chart. Does it show any abnormal events? Well, of course it does. There's one on the averages chart and one on the ranges chart. And special cause variation would be expected, but the variation will be expected to come down within the control limits as I start to practice more. If I practice many times, you'd find the variation comes down within the control limits. But the only way to produce a significantly better quality, in other words, the only way to bring these control limits in closer, is to change the system, to bring about a fundamental change to the system. And this is what happened. In 1898, Admiral Sir Percy Scott found a way to significantly improve the quality of the shooting. And you've got to try and guess what Sir Percy did. And in hundreds of demonstrations, I've never seen anybody that guessed what he did. And all the bright engineers amongst you might have a go at guessing what he did. And this is long before the days of gyroscopes. What did he do to improve quality? Anyway, we implement this and we see a 3D animation of Sir Percy's idea. And then we play the game again and we see how the variation is reduced and the control limits are brought in. So by playing this one game, we learn about histograms, control charts, special causes, how quality can be improved by reducing control limits. And the final part of this exercise is we learn the importance of good communication, because Sir Percy had this massive quality improvement, but nobody believed him. He spent 20 years. Well, no one believed him. The Admiralty had him come and demonstrate his technique on the Admiralty lawn. And when you discover what his technique was, it didn't work on a solid platform like a lawn. And Sir Percy was drummed out of the Navy charged with fraud. And it took 20 years for his idea to be universally accepted. And he was invited back into the Navy. So the final part of good quality is to communicate the ideas. So it's not good enough to have a good idea. It's to make sure it's implemented in the company. How's my time, Roger? Do I have time for one more example?
Um, no, because we
One?
already have a few questions that we need to sort. So,
This is quite a good one because just let me I'll show you it quite quickly.
okay, you
When
could
you
go
have,
ahead.
when you have special causes, the first step is to look for the causes. So you should be looking for causes when you have a problem. But what do people do? What does everybody do when people have a problem? People try solutions. This is not, let's try this. It worked last time. Let's try it. and of course the solution doesn't work. When you have a problem, the first thing to do is look for causes. And this is another historical example of showing the importance of looking for causes. So in the 16th century, handguns had a serious accuracy problem. And these are actual three handguns taken from the time. Not a good solution. Let's try a different solution. Another solution that didn't work. Let's try another one. Why do you think it took them 20 years to improve accuracy? And most people will guess some of these up here. But to move through very quickly, if you think of the exercise, you just think what you're doing in the exercise. You're taking a burning wick and putting the burning wick into the gun, putting the burning wick into the gun's tinderbox. So the cause of the problem was they couldn't aim. They couldn't take aim. And what the solution did, the solution addressed this cause. And all it was just a trigger that put the wick into the tinderbox. So for the very first time, they can take aim. And so I can just drag the gun and move it around here. So I can now take aim because I pull the trigger and the wick is put in the tinderbox for me. So by addressing the cause, they had a massive improvement in the quality of their shooting. Now, I'll hand over to you, Roger, for questions.
Okay, so we're going to address some of the short questions first because we have a few long questions that are actually two parts. I'm actually going to go to this first question. This first question, do tools guarantee good quality?
No. You might recall when I was in my talk, I said Professor Ishikawa's basic tools, if used wisely. So it's the thinking that is the key. The mind comes first, and the tools come second. Using tools wisely is the key. So tools are just an aid. And having 55 tools is just utterly ridiculous. 55 tools won't make quality any better than having 7 tools. Tools are just an aid. And the key tool is control charts. Control charts are the tool that is at the heart of quality. And hand in hand with control charts are histograms, the tool that ISO forgets completely. So histograms and control charts, they're the only tools that are really key. And thinking.
Thank you. Also, going on to our comment by Anthony Martin, it's more like a question. ISO 9001 is a cost of doing business. How do we mitigate against it?
How do you mitigate? Well, ISO is not mandatory. It's just that if you're working with other companies, ISO has reached the point, I think about 1 million people have bought into ISO. So many people are using it. People think it's helping them. And it's sort of become mythology. And so if you're a supplier, the company that your supplier expects it. So it becomes a sort of a mandatory cost of doing business, even though it's probably not going to do a lot for you in terms of quality.
Okay. So on to this next question. It's a two-part, by the way. In many quality and process control settings, specification limits are overlaid on histograms and control charts. Is there a technically accurate approach given the distinct purposes of control limits and specification limits? And what are the potential risks or misconceptions that can arise from this practice?
That's a long question, but specification limits should never appear on a control chart. Similarly, there's no point in showing the 1 sigma limits, 2 sigma limits. You should never have 99%. All that should appear on a control chart is the upper control limit, lower control limit. Specification limits can be shown on a histogram, as I showed you in the example. That's the place for specification limits, and not on the control chart.
So on to our other question, going back to the specification limits, can you discuss some common misinterpretations that occur when specification limits are applied directly to control charts? And how can these misinterpretations affect the insights drawn from such charts, which ultimately impacts decision making?
I think the key thing, putting specification limits on the control chart, it adds no value. Remember, the purpose of the control chart is an action chart to ensure that your process is predictable. Specification limits aren't going to help that at all. Limits aren't relevant in terms of that aim. The aim of the control chart is an action chart to tell, very importantly, control charts aren't intended to be wall art. Lots of people, oh, these are all the control charts of what's happened in the past. The purpose of control charts is a call to action. So control charts should be at the workplace. They should be alerting operators as to when they should investigate something that's gone wrong.
On to our next question, focuses on ISO standards. ISO standards are generally non-prescriptive when it comes to the specific tools used for measurement and process improvement. How does this non-prescriptive nature impact the consistency of quality and process control efforts across organizations?
Well, ISO 10009 is certainly non-prescriptive. It's just a list. So what's the point? I think all up, there's something like 130 tools. They could have listed 130 of them, in addition to the turtle diagrams and OEE. So just having a long list of tools doesn't help you with anything. People need to know what to do. For example, an omission from all the ISO standards is Deming's operational definition. It's not mentioned anywhere. You have a problem. What chart? Let's draw a control chart. Let's draw a run chart. Step one is the operational definition. What are you trying to achieve? Why are you drawing a chart in the first place? What's the point in drawing a chart? Why are you drawing it? Step one is, what are you trying to achieve? And people don't ask that. That is the prescriptive approach to quality. And then, of course, there's PDSA. And most people don't. When I first started in quality, there were dozens of methodologies for quality improvement, and our clients were asking to build them into Q skills. I thought, this is just nuts. There's dozens of them. And then eventually it just got whittled down to fewer and fewer, and Deming and Six Sigma's methodology and Deming's PDSA became the two remaining ones. The difference with PDSA is that PDSA is the scientific method with control charts added at each step. The scientific method is the fundamental methodology for improving anything, quality or anything. And the scientific approach for improving quality is the scientific method plus control charts, which is PDSA.
Okay.
So PDSA plus the operational definition are the prescriptive approach to quality.
So on to our next question. What are some of the common examples where the pursuit of Six Sigma or high control methods have been counterproductive from an economic perspective, as well as how should leaders recognize when to ease back on stringent control measures?
Examples where Six Sigma has been counterproductive. The fundamental problem is any company that embarks on a methodology that was created by a self-confessed con man is doomed. The guy that created this stuff was clueless. He was a high school teacher. I actually wrote to the place where he actually got his education, the Mary Lou Fulton Teachers College. That's where he got his supposed PhD. When he first spoke to Bill Smith, he stated that he had no clue what Smith was talking about because he knew nothing about quality. He was completely ignorant. So any company basing their future on a method created by this con man, for a long time, I wondered whether Six Sigma was just stupidity or whether it was a fraud, because it was just so utterly ridiculous. You saw the graph that I showed of the process of the 1.5 Six Sigma shift in the mean. How on earth could anybody in their right mind see this as being a good thing? And for a long time, I wondered, was this just Harry's stupidity or was it fraud? And then I was very, very fortunate to actually have a chat with a fellow who actually worked with Harry at Motorola. And he said it was fraud from day one. The whole thing was a scam. It was a scam. So any company basing their future on a con man scam, what do you think is going to happen? They're going to end up like the guys at Ford. That fellow the engineer that told me he's seen the 1.5 Sigma shift in all their processes, and he thought this was good. And he was telling me that all their processes were an out of control disaster. And then they wonder why they get 220,000 parts per million defects in successful projects. That's what happens when you build your company on farce.
So on to our next question. There is often a tension between creating a culture of learning and improvement versus a culture focused solely on compliance. How can organizations focus on quality without slipping into a purely compliance-driven mindset?
Well, what are you trying to achieve? Step one, Deming's operational definition. What are you trying to achieve? With compliance, what are you trying to achieve with compliance? The aim with compliance is, if you're a supplier, for example, the aim with compliance is to have the company that's buying your product buy from you. That's all you want, compliance. So it's the operational definition again. What are you trying to achieve with compliance? So you've got to look very, very carefully. Why are you doing it? I was talking about this with Roger at the start. If you've got 94% of the companies in the States run single shift. Now, if you're running single shift, and I said to Roger, Roger, if you had documents documenting your job, you're the only person doing your job. Is a document documenting your job going to help you? Well, of course it isn't. But perhaps if you had two shifts or three shifts and you had operators doing different things, this is very common in the petrochem industry. Each shift operator has their own settings. New shift starts, operators come in, they change all their settings. Each shift operator has their own way of doing things. In that sort of instance, standardization is very helpful. You get everybody doing the same things. Operators are tampering. It's making things worse. So in that instance, standardization is excellent. But the first step is Deming's operational definition. What are you trying to achieve? Are you trying to ensure that the company that you're selling to buys your product? In other words, just a tick. Are you after a tick, or do you really need to standardize things? So that's really what you need to do to determine whether or not standards are important. And certainly standards like 7870 and the ISO 10,000, they are just junk, utter junk. You can throw all those standards out the window.
So on to our next question. In many cases, strict quality control processes can stifle creativity. How can organizations strike a balance between the necessity for control and the flexibility that allows for innovation and adaptability.
Think of the Q School's demonstration of the ship game. Now, I didn't tell you what he did. Have you all been thinking about what that guy did? Now, this is creativity in the extreme. And this is creativity to create a huge quality improvement. So how do you improve? You've got a 1 in 50 hit rate, and the ship's rolling, it's rolling, yawing, pitching, and you're trying to shoot the end. What do? It takes a very, very creative solution. And what he did, because the gun barrel was so heavy, he relied on the inertia of the gun barrel as the ship rolled. So he had his men very rapidly crank the gun barrel attitude adjusted backwards and forwards. So as the ship rolled, the variation in the movement of the gun barrel was reduced. So by reducing variation, he got better quality. Now, I have literally demonstrated this hundreds of times. No one has ever guessed what Sir Percy did. Now, that is creativity for quality. So quality improvement and creativity, they go hand in hand.
All right, so this question is related to the results of the game that I believe. How are the upper and lower control limits derived?
They're calculated from the data. Well, they're calculated from past data. It's accumulated data. And so it's not just the individual's game, that's data that's accumulated over time.
Okay, our next question. Today's topic spoke to reimagining quality. Where is the reimagination or insights for improving quality in my service organization? And what advice do you have to take the quality journey?
Reimagining quality in this instance, you could call back to the future. It started with this group of brilliant statisticians, Dr. Shewhart, Professor Deming, Professor Yoshikawa, Professor Lewis, he was a philosopher, Dr. Wheeler, Dr. Neve, Dr. Taguchi. All these brilliant men laid the foundations of modern quality. Then along came a con man, and everybody has jumped into the con man's nonsense. And then it started to wane after a couple of decades, and so lean was tacked on the end of it. Lean, where does lean come from? Lean started with a book. And the book was called The Machine That Changed the World. And it was like a joke. A political scientist, a civil engineer, and an economist walk into a bar. Instead, these three men walked into Toyota. So they're looking at Toyota. They had no idea what they were looking at. They missed the key things that Toyota was doing. Toyota's methods were based on Deming. Toyota's quality circles are based on Deming's methods. They missed it. Okay, it is actually mentioned, but they didn't realise how important it was. So reimagining quality is going back to quality's roots with these brilliant men that laid the foundations of modern quality. So it's a matter of getting past all the fads. Quality has had 20 fads in 70 years. Zero defects, Six Sigma, quality 4.0, quality 5.0. I cannot understand why so many people are so gullible and buy into so many fads. I'm a chemical engineer, as you probably know. If someone came into my office and said, "Oh, we've got this new approach to chemical engineering. It's called chemical engineering 4.0, chemical engineering 5.0," any chemical engineer would just kick them out on the street. But quality people invite them in. Oh, yeah, that sounds great. Let's go. Let's buy the quality 4.0. Let's buy the quality 5.0. Let's buy into the latest nonsense. There was a guy just a couple of days ago, lean agile, just nuts. Agile, by the way, derived from about 40 odd years ago from what was his name? Anyway, but it came from RIP, R-I-P, R-A-D and R-A-B. These were software development methodology fads. And then it became agile. And then someone had the bright idea of calling it quality. Just nuts. So to reinvent quality. It's to go back to the future, go back to the fundamentals, go back to the fundamentals laid by Deming, Shewhart, Wheeler. That's what reimagining quality is all about. Forget the fads. Forget the nonsense.
Okay, so I would like to just highlight a comment, two comments actually from Ute Wish. I hope I got your name correct. The new revision of ISO 9001 will be released most likely in 2025. Still, this quality thinking is not included. And he also mentioned that how can we shift successfully this quality mindset thinking to top management?
Okay, I'll say a word on the latest ISO standard. It's bringing in global warming. I think, oh, for heaven's sake, just just nonsense on nonsense. And the last part of the question, how can we educate management? I'm sorry, could you repeat the last part of that question, please?
How can we shift successfully this quality mindset to top management?
That is the golden question. In 1982, you had a CEO at Ford, Peterson, was it Patterson? Patterson, Peterson, I don't know. But the company was going down the tubes. They were on the verge of bankruptcy. And he was a CEO who was smart enough to recognize what Deming could do. So he brought Deming into the company. And Deming turned the company around. And then just a few years later, that CEO left, new CEO comes in, and he buys from Harry, buys from Conman Harry. And of course, the company goes down the tubes again. And they're still doing antiquated quality. They did not learn their lesson from Deming. So the problem is you need senior managers who are aware, who are educated, who understand quality. Look at Boeing. Boeing quality has gone down. They were an engineering company, and quality has gone down the gurgler. And the reason, they've had a succession of companies, a succession of CEOs who were economists, accountants. They've got all they were interested in is cost cutting. They want to cut costs. So along comes Six Sigma. We'll help you cut costs. So Boeing dives into Six Sigma. Dear, oh dear. And then you end up with the CEO killing 346 people in the 737 MAX crashes because they abandoned quality. So how to educate CEOs? If anybody can help me, I've got no idea. I've got no idea.
Okay, so we are on to our final question. Well, those are two parts, but I believe the first part is very important. We will treat this as the last question. How can leaders instill a sense of ownership in quality and performance beyond the myth of Six Sigma certifications or the process? And does the sense of ownership differ in part compared to its strict adherence to a system? I treat it as one question.
Absolute, very, very good question. And this is sort of a question that's on the money. Do what Toyota has done. Don't copy. Do not copy Toyota. Copying is the worst thing you can possibly do. Deming said, just because something works well for one company doesn't mean to say it's going to work for you. But what Toyota did was to apply Deming's principles. And the key in this context is to engage employees. Every Toyota employee is trained in quality. They don't sort of have levels of coloured belts and having clowns with coloured belts running around telling workers how to suck eggs. They engage everybody. So everybody is equally important in quality, especially the frontline workers. If you're going to make a quality product, the guy sitting up in a desk in an office somewhere, what's he going to do? It's the guys at the front line that are key. They're the guys that are actually making stuff or interacting with service industries, interacting with customers. They're the people where quality really happens. So it's engaging those frontline people and not alienating them, making them feel important. Train them. That final slide I had with Toyota Quality Circles training. Get them all engaged. Train the workers and don't alienate them. Make them part of the system.